Correct. We're going to get this product here. Why? Which cation? You'll make cation on top or bottom. You're going to make cation on bottom. Why? Because it's resonance stabilized. You can draw resonance structure. Okay. Cation on left or right. Going to be on the left, yeah. UH there, cation here. This cation is resonance stabilized a good bit. What's the name of this type of cation? Benzylic cation, very resonance stabilized. And the iodine will end up attacking there. If we made the cation on the other carbon, that is H added here and cation there, does that have any resonance? Is that cation resonance stabilized or resonance delocalized? Can you draw a resonance structure? The answer is no. Also, is there another p orbital conjugated with this p orbital? No. This carbon does not have a p orbital. That carbon does not have a p orbital. There's no conjugation. There's no resonance. Lots of resonance here. More stabilized. So not this cation. This one, iodide adds here. You get that product there. So choosing the correct cation, we now can include resonance as a consideration. Which amino group of the two compounds above is most electron rich? How do we do? Top or bottom?
Top.
Who's that?
Top.
Top? Did anybody say bottom? Yes, top. Any questions on that one?
Yes, why is it the top one?
Less resonance. Did you draw resonance structures? How many resonance structures did you get for the top?
I got two.
2? Maybe you should have gotten more than 2. How many did you get to the bottom?
Same.
No, for the bottom one you should have gotten
Like 4.
like 4. Why didn't you get 4?
I don't know. I must have done something wrong.
Gonna look up?
Oh, they're in my notebook at home.
Okay. Any other questions about those? Other questions about those? Wrong page. Anybody attempt those? Okay, let's look below. Delocalization of pi bonds. Here we go. Neutral molecules. Where are B? What are we under? What was A and B under? Neutral molecules. Neutral molecule here. Here we have a pi bond that we can polarize, but we have an oxygen. We have a dipole. The pi bond is very polarizable. We can do resonance with the pi bond. We can move electrons towards the oxygen. Because you wouldn't want to move electrons away from the oxygen in this case. That polarization gives that resonance structure. Just move the pi bond up.
I see.
Polarization of the pi bond to heteroatom oxygen. Electrons moving up to oxygen. What type of orbital are these lone pairs in? Are these lone pairs conjugated with anything here? What type of orbital is, the answer is the same. This is in what type of orbital?
SB2.
Yes, sp2. Would those electrons thus be involved in resonance? No, right? Why no?
They're not in the p orbital.
Because they're not in p orbital. Only electrons in p orbitals would ever be involved in any resonance. If they ain't involved in it, if they're not in a p orbital, you don't do anything with them. Right? No. Off limits. All I moved is the pi electrons. That is the 2 electrons in the pi bond. I just polarized them up onto the oxygen. Because of this right here. The electrons want to go towards the oxygen. That's an example of that. Very representative of carbonyl. What's the true structure here? Do we have any other resonance structures that we can draw before we consider the hybrid? No other resonance structures. What's the true structure? What's the bond order between the C and the O? Somewhere in between. What's in between 1 and 2? 1.5. What's the charge of the oxygen in the hybrid?
Partial negative.
Partial negative, and the carbon?
Partial positive.
If you could look at acetone, there's acetone on the right. That's the true structure. That is, the electrons in the pi bond are really closer to the oxygen. And we got a pinky bond in between here, yeah? But it's not like a no bond, there's only a one bond, because here you got a lot of charge, and so these electrons are going to have some attraction down here. So this is illustrating that. We used the 2 fake resonance structures though. Show all possible resonance structures for the cation above. How many additional resonance structures did you get here? This is 1. How many additional did you get? How many? Who's that? 2 additional?
Yeah.
Or a total of 3?
Yeah.
But let me ask you this. Here are the charges on carbon in your resonance structures.
Just one.
Do it?
Just one. Yeah.
I thought you said 2.
Yeah, one's wrong. So it's just one.
1 additional. And the positive charge is on what atom?
Fluorine.
Okay. We have a lone pair. How do you stabilize a cation? Move electrons towards it. We can get a resonance structure there. And that is A arrow, A arrow. You can do that, but I thought.
I thought you would do oxygen would be more. Fluorine wouldn't want to be positive like at all. It's more that you're able to get oxygen, right?
I think I would look at golden rule number 4. Golden rule number 4. Can we put a positive charge on this fluorine? Yes, as long as it has what? As long as it has an octet. Does it have an octet there? Yes. Okay. Was there another resonance structure we could possibly draw? Move to what? Let's see. That resonance structure is positive. Now you have a resonance structure that's negative. I refer to number 3. All resonance structures have the same net charge, right? How about if we take these electrons and move them here? What would that get? Give that there. That's
Isn't that what you're saying, it doesn't have an octet now?
exactly. No octet. No octet. So can we do this? No octet. No octet for oxygen or something that's electronegative. Kimber, you drew this, but somehow you had 3 lone pairs there. And you put a negative charge. There's only 2 lone pairs there. Where did the 3rd lone pair come from? It ain't there. Thus, that's a positive charge. It's indeed still positive like that. The problem is no octet. This oxygen will hunt you down and make you faint. No good. If this was an alkene, a carbon-carbon double bond, we could do this and we can leave the carbon positive. This is what we did before. Carbon positive with no octet. But never leave oxygen or fluorine or anything like that positive with no octet. Nitrogen. Here it has an octet. That's okay. 2 resonance structures on the board. No others. Which one's major?
Oh, the second one.
That's actually also the major. Even though the charge is on F, it's okay. It's got more bonds. Okay, over here is just mainly a little review. Acid-base chemistry. We looked at this during test 1. I may have showed this exact 3 compounds. Carboxylic acid is more acidic. You'd be able to explain the rationale there. Compound below, which is more acidic. Now this is going to involve drawing resonance structures. And the only difference, of course, is the location of the nitro group. Called a nitro, like nitroglycerin. You'll see nitro group in organic 2. Lewis structure for nitro, coming off the ring. Nitrogen, double bond to O, single bond to O. This oxygen being negative, lone pair, standard oxygen. The nitrogen is positive. So the functional group is net neutral. There's no way to draw it without charges, though. But it is net neutral. But you have pi bond here, well, in this fake structure, because you can draw resonance of the nitro group. But you need to be able to draw resonance structures. This is just like the one before. Okay. Effect on basicity. Looking at nitrogens, because usually if you're looking at a neutral molecule, Just about the only thing that's going to be basic is a nitrogen. We could be looking at anions, but these are all neutral nitrogens. Which nitrogen is going to be more basic? The one that's more electron rich or less electron rich? More electron rich, attacking the H+. Okay. The question is really what we're getting at, which nitrogen is more electron rich? Just like the one on the previous page. Or down here, which nitrogen is more electron rich? How many pi electrons in the compound below? Anybody get an answer there? Anybody get an answer to that one? Anybody not get a green handout on Wednesday or Friday? Please come pick one up. Okay, chemistry of dienes. Warm-up page here. Some questions, various topics that are deemed important. Can a different product be obtained from a chemical reaction based solely on the temperature of the reaction? For example, here, if we treat this with HBr cold versus hot, we will get different products. Yes? Why would you say yes?
Because if it's not thermodynamically favored, then the cold is not going to...
What?
If it's not thermodynamically favored, then the hot reaction is going to push it towards happening, whereas the cold wouldn't.
Well, it sounds like you're arguing one will happen and one will not. The question was really, when you get different products, product meaning that it happens in both cases, but will they be different outcomes? Okay, chemistry of dienes. Conjugated versus non-conjugated versus cumulated. We've already covered that on the previous handout. Let's look at nomenclature of dienes. Pretty straightforward. We're looking at alkenes, but with two, diene. This would be a diene here, right? So we're going to look at the chemistry of these a little bit. Nomenclature, very similar to before. Longest continuous chain, 1, 2, 3, 4, 5, 6, 7. So we got a hep. If it was just one ene, it'd be like a heptene. We're going to call this a heptadiene. It's got two enes. Now we got to indicate where the enes are at. This would be the one position, correct? 2, 3, 4. 2, 4. Heptadiene. That seem reasonable? Indicating where each ene is at. What else do we need to do here? What's the name of the next compound?
Cis 2,4 heptadiene.
Same exact name, right? What's it difference in these two? They're stereoisomers, yes. This name, we need to indicate the configuration of the double bonds. Stereochemistry. This one is that E or Z? E. How about this one? Both of them are E. E, comma, E. A lot of times you put this in parentheses. What do you want to call this one here?
Z, comma, E.
Z, comma, E. And then the same exact name. Because stereoisomers have the same exact name. They only differ by what? Some type of stereochemical descriptor in the front. Don't forget your easy, yeah? Now typically when you list these, the first one is for the first ene and the second one is for the second ene. So the Z is for the implied to be at the lower ene, the 2, and then that's the 4, right? What's the name of the compound on the end? Name that compound.
So there's actually a longer parent chain that doesn't have the two, so you want to pick one with both of them being in the chain, right?
Well, when you name this monoenes, the alkene needs to be in the longest chain. Yes, with dienes, both need to be in the longest chain.
Easy.
Now, that can get a little complicated because you may have some choices. I mean, both ways contain enes, and they can't both be there. So, but we're not going to go there.
Okay.
For what we're doing, both need. So basically, this is the longest continuous chain here. So that's the only chain where both alkenes are in. What is that? 1, 2, 3, 4, 5, 6. Hexadiene. What are the numbers? What is the positioning of the double bonds?
1 and 2. And 1 and 5.
1, comma 5. That still doesn't tell us which end is number 1. Which end is number 1, left or right?
Right.
Correct, right? That's 1, that's 5. How do we finish this off?
1 chloro, 3 chocolate.
1 chloro,
Oh, yeah,
3 propyl.
it's 2, I'm sorry.
Two purple.
It's 2.
2 purple.
I
Sorry.
messed up.
2 propyl. 1 chloro, 2 propyl. See, the reason this is 1,5, you get 1,5 either way you go on here. That's the one end because the substituents will be 1, 2. If this was the one end, it still would have been 1,5, but the substituents would have been 5, 6. So that's why we chose the right end to be number 1 end. Do we need anything else? How about an E in front?
Do you mess with the terminal alkene at all?
Does it need to be named? The E refers to which alkene?
First one.
The one that's stereogenic. Right? Do we need a second E or Z? No, this alkene is here, this alkene's not stereogenic, right? All alkenes up here are stereogenic except for that one. So we did not need an E or Z. How's the nomenclature look? Should be pretty straightforward. Consistent? Miscellaneous thing before we move on. One application of dienes is isoprene. It's very simple diene, the methyl substituent. You can name 2-methyl-1,3-butadiene. Neither alkene is stereogenic, so you don't need anything in front of this name. But this is more commonly known as isoprene. And isoprene is a building block in nature for a lot of natural products, such as limonene. Where do you find limonene at?
Lemons.
Yes, in lemons. Lots of different compounds out there. Limonene is made from isoprene units, and it is a polymerization. Now, it may not be a huge polymer. In fact, this is only a dimer to get here. C5H8, the formula has been doubled. Okay? This is a building block that plants use to then make larger, very sophisticated and useful compounds, such as retinol. Now, first off, terminology. This guy is known as a terpene. A terpene comes from isoprene. Now, if it's a straight just dimer or trimer or polymer, that's a hydrocarbon, so this is going to be just a hydrocarbon. That's all it is. Just hydrogen and carbon. C5H8, we multiply each of those by 4, we can get C20H32. It's where 4 units came together. Mechanism, could you do a mechanism from going from here to here, 4 units? I don't know, it's pretty sophisticated, but it's probably it's all old-fashioned, just carbocation chemistry, ring formations, etc. It's amazing. This includes oxygen, so that's not an exactly dimer or trimer. Where did the oxygen come from, etc.? Well, sometimes you can get to such a product, and then maybe you can hydrate one of the alkenes, and that's probably maybe what's happened here. So it's not exactly coming from that, but something has changed. This is called a terpenoid. What does an oid mean? Like humanoid?
Like,
Human-like? So it's not exactly a terpene, but it's terpene-like. So it's called a terpenoid. Because it's not exactly a multiple of that. But that's where it came from. Some important compounds up here, including squalene. That's in some of your fungi. Fungi? I don't know how you say it. Mushrooms. Also in fungus like fungus that grows between your toes. Something that you don't keep it clean, I don't know. That type of fungus. And then you can treat that fungus with medications like, what do they call them?
Antifungal.
Lamisil or something? Fungal cream? Fungal cream has a compound that inhibits squalene epoxidase. What is squalene epoxidase? It's an enzyme that causes one of these double bonds to become an epoxide. And it leads to building up the fungal cell wall. The fungal have cell walls. Squalene is a component to cell walls, and the drug inhibits that process from continuing and eventually kills the fungus. Beta-carotene, okay? I think that's an exact multiple of isoprene. Have y'all seen these in biology?
yeah,
Terpenes, terpenoids?
in passing.
Okay, they all come from just a very simple diene, okay? Including like Taxol, breast cancer drug. It's a little dark here, but Taxol was first isolated from the yew tree. This is an old yew tree. This is some person with like an axe just cutting into the wood. It's amazing how that tree is also a chemical factory. All starts with isoprene. Well, how is isoprene made? I think that's made from like CO2, right? Don't plants take in carbon dioxide? That's where the carbons come from. So you can even go back to that. Chemistry of dienes. Okay, 1,2 addition, also called direct addition. We take this diene and react it with HBr. Okay, we're doing our very similar double bond chemistry. We can get just addition of HBr. Mechanism there, what's going on? Obviously the alkene on the left has reacted. What if we reacted the alkene on the right? It would be the same product. This is a symmetrical diene. Any difference between this carbon and this carbon? No. Any difference between that one and that one? No, not in this case. So I do either one. Let's focus in on here since that's where I reacted at. Where are we going to make cation at? Left or right? On the right. So H plus. This comes here. We got H on the end, and we get that cation, right? Now maybe you're like me and you'd rather just not even draw in this new H because it looks funny. Anybody like me? It's there, right? I hope you all see how to get the final product, right? Br minus, which is here, yeah? Nothing new, yeah? Some terminology, though, that we'll bring in. This is called a 1,2 addition. The new H is here. The new H is there. Bromine ends up next door. If this is 1, then what do you want to call the next door carbon? 2. So things have added in a 1,2 relationship. We've also done an addition because we've added HBr. So this is an example of a 1,2 addition. It's also known as a direct addition. We'll explain further why. All those reactions we did for the past months, those were all 1,2 additions. They were all direct additions. We just didn't use this terminology. Now, before we go on and finish this up, when you see such a cation, what can you show here or think about?
Resonance.
You see some resonance? Yes. Resonance structure. The old windshield wiper. I bond here, cation there. I'll continue to draw in the H since I've got it drawn in the product. Resonance structure, yeah? So the cation is resonance stabilized, our intermediate. But the final product comes from what? This attacking here. Right? Now, why did we draw the hybrid and attack the hybrid? What does the hybrid look like? Boom, boom, boom. Boom. Partial plus, partial plus.
On the primary.
Do what?
Primary carbons, it's less stable.
The H here. What about the primary carbon?
Well, the cation on the end, it's less stable than.
Well, you got to be careful because it's just this. You're kind of acting like it's two different cations.
Is it
Or
because
perhaps you're just considering which one's more major, so you got to kind of clarify, but this is the only intermediate, right? This is your only intermediate. I mean, that's what this is. This is two fake representations of that.
is it because the left is more positive, whereas those are partial positives? Maybe the does that have any effect?
Now, what I'm getting at is, why didn't we draw the hybrid and attack the hybrid? The answer is it's cumbersome to use this in a mechanism. I mean, what do I do? Where do I move the electrons? So instead of working with hybrids, we need to be able to show them and understand. We work with these fake structures instead. Problem is, you guys usually think this is two intermediates, right? This is only one thing up here at this point. And we work with the fake structures. But I did a 1,2, that is the bromine added here. All right, let's look at the reaction below. Try to keep it up there. Now that's your outcome with cold temperature. Like minus 78 degrees, that's pretty cold, you know? If you do this reaction with higher temperature, like a little warming, 40 degrees or even higher, same exact reaction, we end up with the bromine out here as the major product. First off, this is a 1,4 addition. Because if we look at this product, we've added HBr. Where's the H at? It's on the end. Because there's 3 H's there, but here there was only 2. So if the H added here, let's call that 1. If that's 1, what do you want to call the carbon with the bromine? 4. So we did a 1,4 addition. And we've not done that before. 1,4 addition is also called a conjugate addition. How do you think we get this product? The beginning is the exact same. We get the same cation. But instead of the bromide adding here, it adds where?
There.
It adds to this resonance structure.
So it goes windshield wiper over to that second alkene whatever you call it, over to the plus cation.
Yeah, that's how we got this resonance structure.
And isn't that what's happening down there with the heat?
No. No, it happened above also. That's why it's already on the board. You got to remember that us doing that is us on the board. The first reaction involved that reacting with H plus to form what?
Cation.
Right here.
Yeah.
To form this. We just chose to, on the board, show a fake structure and then show another fake structure. But it's just this. Now, we could come over here. Here's your intermediate for both reactions. Br minus could add here or it could add here. That's how you get your two products. But again, this is cumbersome to work with. It's much easier to do it with each of these fake structures. Addition to fake structure, okay? And us showing the two is not a step. And again, saying that that only took place with heat, that's just not right, because it takes place as soon as it is formed, it's there. This is called a 1,4 addition, conjugate addition. The conjugate comes from the fact that the cation is conjugated. And we're really invoking the conjugated cation, or starting to work with it. All right. The first outcome is called the kinetic product. It's formed first because it's formed fastest. This is your common intermediate. Okay? It's formed by the alkene reacting with HBr, right? That comes over here and gives that over there. Boom, cation here. But it's a hybrid. At this point, where's the Br minus? The Br minus is next to the H plus. Even though they're ionized, they're still attracted to each other. And so if the H plus is over here, Br minus is going to be over here. Now it attacks. And it can attack either cation. Which one's going to be faster? Attacking here? I'm going to erase these zeros. Or attacking there. Which one's faster? First one. Why? Because it was closer. That's called a proximity effect. It just attacks it closer. It's faster because it's closer. Who can I slap hands with? Her or him? Sorry, this is just faster. That's what we're saying here. It's faster. That's called the kinetic product when you talk about rate. Which product is more stable, though? The two products are shown. Cold product, heated product. Which one's more stable? Top or bottom? Bottom, why? Disubstituted alkene. That's a monosubstituted alkene. More stable. So this is the thermodynamic product. Which means it's the more stable product. Right? So this is fast. This is slow. But attack here gives the more stable product. It's just slower. Now, we got to be careful moving forward. Some of you guys always want to think that the 1,4 product is always the thermodynamic product. It's not always. Just in this example. Okay, let's look at over reaction coordinate diagram for these two. Now we actually looked at this in the handout when we started alkene chemistry, this exact diagram. We said we would look at it later. It's now later. This is the exact reaction. It's just shown sort of partially condensed. Have a transition state leading to a common intermediate. Here's your common intermediate. Unless you want to just focus in on the two fake structures, which sometimes is easier. As long as you know they're fake, they're easy to work with. But right now, I'll just focus in on the hybrid. The hybrid is your common intermediate, right? From there, we can get two different outcomes. 1,2 or 1,4 product. Which one's more stable in this case? The 1,4. We explained why. So it's lower. Which one, though, is easier to get to? A transition state. 1,2 is easier to get to because it's just faster. So what we have is two different transition state energies. The energy it takes to do the reaction to get here. 1,2 is lower. But here it's the higher energy product though. To get to the more stable product, you have a higher transition state because why? It requires a cross-country trip. That is, this bromine has to go way over there. And that's a lot of energy that goes into that step. Thus you need more energy, it requires more energy, it consumes more energy for that cross-country trip. Now this, earlier on, we said that this is a little bit odd because usually we said the lower energy products is usually going to have a lower transition state. But this ain't the case here, is it? The lower energy product has the higher transition state here. Making sense?
Do you only get that product with heat? Or do you
I only get it with heat, but let's explain why. Thank you, because that's my next.
No, I guess I meant more, do you get a mixture of the products when you use heat? You don't just get 100% the NBR.
Well, hardly in any reaction we've ever done do you get 100%. Usually we're looking at major product.
It is the major.
Yeah, major product. Why with heat? Okay, let's do it cold. Limited amount of energy, right, when it's cold? Here we go, it's real cold. Or whatever, it doesn't have to be cold. Which way is it going to go? Why would it go uphill if it can go downhill? You see water running down the road. It's got a choice. Is it going to go down the hill or up the hill? It's going to go down the hill, right? So that's why you get this product, first and fastest. How do you get, why does heat give the other one? Because with heat, and it's explained here I think in text, with heat you can establish an equilibrium between the two. Because with heat, you can drive it back, and it's reversible. You can go back up here. It's reversible. Now we'll talk about being reversible in a few more days. Reversible. And with a lot of heat, yeah, it can reverse and go back. But with a lot of heat, it can also go over. It's like a hurricane. You got water coming down the road, and you got two forks. It's always going to go this way. What if it's a hurricane with lots of heat, lots of water, lots of wind? Will it go this way some? Yeah, but it's going to take a lot of water, okay, a tsunami coming through to get the water to go this way. Well, that's what heat does here. It gives it enough to go there. It pushes it over. Well, it can come back if there's enough heat. But at this point, we have an equilibrium. And here's the key thing. Whenever you have an equilibrium, you're now driven by thermodynamics. And when you have an equilibrium, the most stable product is going to be favored. Which is the most stable product? 1,4. If we can establish equilibrium by giving lots of heat, then the 1,4 will become favored. But it was never formed first, and it was never formed fastest. We'll see what type of questions we have on Wednesday lab this week. We're doing dehydration of the alkyne. Today it is a group lab and a group report. So what type of questions you have on Wednesday?
Are we meeting upstairs?